Export into the cloud. Okay, Reed, if you're there, can you hear me? This is not sharing screen. Why is that showing me? I don't want that to show me. What's going on here? Reed, I don't think you can see. How do I make it so me? Can I share screen correctly? I can see N here, but can you see the paper? Is it showing something else up here? Maybe I need to just take me off. Yes, I see the paper. Fantastic. Then, okay, then we're good. I don't know what's showing me. Let's hide that. Okay, I probably will have your tests next time. God, if I don't have them graded after a 4-day weekend, I don't know when I'll grade them. But I swear they're like rabbits. Every time I turn around, there's more in that stack. I don't know what's going on there. Today is November 23rd. Come on, pencil, work for me. We are going to talk about stuff in chapter 7 for this time and next time. I do want to announce your final exam. I hope I get this right because I forgot to look it up. It is Tuesday. Does that sound like December 7th? Anybody ever look at that exam? I think it's 7th. It's at 10:30 a.m. And you and my other trig class will be together, and so we won't fit in here. They've moved us to the biology lecture hall, that one right outside the door here, biology lecture hall 100. So as you exit this building, you see that kind of hexagonal room, and that's a little bit larger than this. So it is in biology lecture hall 100. I imagine if you get lost on that day, I'll be able to find you. It goes from 10:30 until 1. And I'll be making the exam, so it'll look like your other ones, probably look closer to the last one, where I don't think I'm gonna, I mean, it takes too long to make multiple choice questions. They just take forever and it doesn't help you any. What I hope to do is put your other 3 exams and this new material and put about 3 or 4 questions from each exam, very similar. I might change a sine to a cosine or change a pi over 4 to a pi over 3. It's about 3 or 4 problems from your previous tests. And then this new material, we're going to have something called the law of sines, something called the law of cosines. And so that's how I intend to make your test, and I hope to do it soon. So about 3 to 4 questions each from each test of exam 1, exam 2, exam 3, plus the problem dealing with the law of sines and the law of cosines. So I anticipate somewhere in the neighborhood of a dozen problems-ish. You know, if I put parts, you know, the parts where I ask for sine of 120 degrees and cosine of pi over 6, that kind of thing. Test 3 grades hopefully will be this weekend, maybe. I know that this week is the last day for drops. So if anybody is concerned about whether or not this test would convince them one way or the other to drop the class, send me an email and I'll have it graded today. Any questions? I will post the old exams keys on Blackboard so that you can look at any corrections and study the correct way to do problems. But I always try to make the final so that it is easier than your other exams, because I know that you're burdened with other courses and other tests and wanting to get out of here. And it is the last day of finals. Okay, let's go. Let's talk about the law of sines and the law of cosines. In chapter, it may have been chapter 3, we talked about solving right triangles. Duh, a right triangle has a 90-degree angle, and we can use our right triangle trigonometry to find the lengths of sides, and we can use the fact that any triangle has their angles add up to how many degrees? 180. So we can solve a triangle, meaning find all 3 angles and the lengths of all 3 sides using our right triangle trigonometry. If the triangle's not a right triangle, we have these 2 things to help us. Triangles that are not right triangles are called oblique triangles. So we will cover 7.1, 7.2, 7.3, and kind of bleed it all together. Okay, so we're looking at, in this chapter, we will be given the means to solve oblique triangles. And an oblique triangle is a triangle that is not a right triangle. We'll identify which of these 2 rules to use based upon some triangle congruence theorems that have been around since, oh geez, the beginning of mathematics. 2 triangles are congruent if all 6 of their parts are identical. The angle from this triangle matches the angle from that triangle. This angle matches that angle. This angle matches that angle. This side has the same length as this side, and so on, so that all 6 pieces are pairwise congruent. 2 triangles are congruent if they have the same size and shape. And so if I draw you a couple of oblique triangles, and let's put another one over here. I'm going to name the triangles by their vertices using capital letters. And so here I'll name this triangle A, B, C, and let's call this one M, N, O. We would say that triangle ABC is congruent to triangle MNO if angle A is congruent to angle M. That one has the same measure as that one. Angle B is congruent to angle N. So I mark that with a different marking. Angle C is congruent to angle O here. Then I'm going to name the sides opposite the angles with the same letter but of lowercase. So the side opposite angle A will be lowercase a. Lowercase b is here, and then this would be lowercase c. Kind of hard to see the difference between the lowercase c's. So maybe I'll put these two little ridges on my capital C. Then little m, little n, and a little o, I'll put a loop on it. And so we'd say that side A has the same length as side M. Side B has the same length as side N, and side C has the same length as side O. Parts are congruent, measures are equal, so I'll use our little congruent symbol, which looks like equals with a similar side up there. Fortunately for us, we don't have to check if all 6 parts are pairwise congruent. We can break down our triangle congruencies into 3 triangle congruence axioms. If these 3 things match, then we know the triangles are congruent. We have 3 triangle congruence axioms. The first one we'll call side, side, side. And we'll abbreviate it SSS. It says if we're going to build triangles, and I give you 3 sides, if I hand you 3 sides and say, make a triangle out of this, and everybody gets matching pieces, every one of us will have the same triangle. There's only one way to put together a triangle in which you have all 3 matching pieces. One and only one triangle. So let's see if I can put it together. If I handed you the same sticks, everybody would have the same triangle, maybe in a different permutation, but we'd be able to line all of our triangles up. Everybody make the same one. So if 3 sides of one triangle are congruent correspondingly to 3 sides of another triangle, then the 2 triangles are congruent. Another way of saying this is you can say that the sides uniquely describe a triangle. The second one is side, angle, side. And so if I hand you 2 lengths and I say, in between those 2 lengths, put an angle of a certain measure. Let's say we put a 45-degree angle in between them. So everybody has the same 2 lengths and a 45-degree angle between them. The angle between the given sides is called the included angle. Then there's only one way to complete the triangle. Every one of us would have to measure a stick that long to complete the triangle. Okay. So if the side, the included angle, and then the adjacent side of one triangle match those same 3 parts of another triangle, then the 2 triangles are congruent. If side, included angle, INCLUDE DED angle and adjacent side are congruent in two triangles, then the triangles are congruent. And the third one, page 2, the third triangle congruence is angle, side, angle. The side here is included between two angles. So I'll give you a side and say, build me a triangle, say that has a 40-degree angle here and a 60-degree angle there. So angle, side, angle. Put a 40-degree angle here and a 60-degree angle here. Then the sides have to have a length so that they meet up at a third vertex. And there's no other way around it. So if I specify the angle size there and the angle size here, then there's only one triangle that can be built. It has to have that length where the vertices meet. Okay, so given an angle, included side, and then an angle, there's only one triangle possible. So here's a picture of what we have. On the side, I guess that's pretty self-explanatory. If I know the measure here, and I know a measure here, then there's only one measure that can go there. Doesn't satisfy the Pythagorean theorem anymore, but let me take the numbers away. Let me just draw the triangles and make the marks. These no longer satisfy the Pythagorean theorem because that's a right triangle operation. So that makes these two congruent. That's the side. Then the side angle, side, angle, side. You see there's only one line I could draw to finish those two triangles, and it has to be the same. Makes those congruent. Side, angle, side. Then the other one was angle, side, angle. Given a side and a set angle here and a set angle there, then there's only one way to complete this triangle, and that's that way. So that side, that angle makes the same triangle. There is no angle congruence theorem. Let me give you a for instance. You know, in an equilateral triangle, all of the angles are 60 degrees. But I can draw you several equilateral triangles that are of different sizes. So knowing the three angles isn't enough to generate congruent triangles. There are all kinds of different sized equilateral triangles. The other permutation that's left off of here is angle, side, side. Angle, side sometimes makes congruent triangles. We don't have that as a theorem because kids learn geometry in middle school and they'll just joke when they see that. I guess we could have called it side, angle, but then you'd never remember it. Angle, side is not a theorem because if I specify an angle, so ignore this length. I'd say I have a measure of an angle, and then I know a side here, and I know a side here, then there could be possibly one triangle. But if this side is shorter, there could be another triangle. So it just depends on the measures given. Angle side is going to be called our ambiguous case. There could be a unique pair of congruent triangles, or there could be a unique triangle with the measurements given in that order. There could be two, and there could be none. So we could have a unique triangle, could have two triangles, and it's possible we could have no triangles. So I'll show you that. That's in section 7.2. I'll show you how that could possibly happen. It's easier to see when you have numbers than when you have that. So there's no angle, and there's no angle side sometimes. I guess it's dead. Okay, so first, the law of sines. When we solve a triangle, we find all 6 parts. And again, I name them with capital letters, and I usually go around in this order so that we all talk about the same triangle. Go, what is that, clockwise, starting with the bottom left. The law of sines says that the measure of an angle to the opposite side is proportional all the way around the triangle. The measure of an angle to the opposite side is proportional all the way around the triangle. It's easier said like this. The measure of angle A, let's go with sides. The length of side A compared to the sine of the angle is equal, that's what we mean by proportional, to the measure of angle B to the sine of angle B, and that's equal to the measure of side C to the sine of side C. That's true for any triangle, not just oblique triangles. That generates the Pythagorean theorem when you have a right triangle. Because in a right triangle, one of the angles, A, B, or C, will be 90 degrees. And the sine of 90 degrees is 1. And that'll generate the Pythagorean theorem. And see why it's called the law of sines. We can also tip them upside down. I could say the sine of angle A is to side A, as the sine of angle B is to side B, as the sine of angle C is to side C. Whichever helps me the most. So that's a biggie. I'll put it in a cute little cloud. And now we'll look at an example. Probably needed a calculator. Okay, so here's our example. Let me do it on the next page. Find sides B, C, and angle C if the measure of angle A is 32 degrees, the measure of angle B is 81.8 degrees, and the length of side A is 42.9 centimeters. So I'll put them in the picture. There it is in words. And in the picture, we have this. And maybe I'm not drawing it to size. I just draw the generic triangle ABC. You're told that this angle is 32 degrees. This angle is 81.8 degrees. Side A is over here, opposite angle A. And that's all we know. We want to find the other three parts. Which of the three triangle congruence theorems do you have represented in this picture? You can either call it side, angle, angle, or angle, angle, side. I think I called it angle, angle, side. Call it angle, angle, side. Oh. Well, this is angle, angle, side. Did I not write that one down? Did I do one of them twice? I did side, 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 angle, side, angle, side, angle. Huh. I guess we'll say there's 4 triangle congruence theorems because I know this is one. Let's put a fourth. Fourth one. Angle, angle, side. So given consecutive angles and then the adjacent side. There's only one triangle. So 4 of them. Side, 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 angle, side, angle, side, angle, and angle, angle, side. We put them down here. Side, side, side. For this one, we'll have to use the law of cosines. Side, angle, side, angle, side, angle, 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 side. And depending, I think we can use the law of sines on these. And then the one we said that was ambiguous was angle, angle, side. Oops, say it again, angle, side, side. Angle, side, side is the ambiguous case. Angle, angle, angle does prove similarity, but not congruency. So if you are given 2 angles, like we are here, the easiest thing to do, you know, is to get the other angle. Because no matter what kind of triangle you have, the sum of the interior angles is 180 degrees. So first, find angle C using the sum of the interior angles is 180 degrees. So I'm going to add the measures of those 2 angles together, take that sum away from 180, and that'll be the measure of angle C. So angle C will be 180 minus the sum of these 2 numbers. So let's see, 32 plus 81.8 leaves me an 8 here. 2 plus 1 is 3. 8 plus 3 is 11. So if I write that as, let me line it up here. I don't think I have any number skills today. So I get to take that, give me a 0.2 here, 6, 6, 66.2. Put it in a box. We're 1/3 of the way done. I think the next thing I'm going to do, I have side A. I think I can find side B pretty easily. So if I want side B and I have side A, then what I'm going to do is use the first part right here. I'm going to set these two equal to one another. So next, second, we'll get side B using the fact that side A divided by the sine of angle A will be equal to side B divided by the sine of angle B. We have 3 of the numbers available to us here. Side A had 42.9 centimeters of length. Angle A is 32 degrees. Side B is what we're looking for. Angle B is 81.8 degrees. So we know all those numbers. You would whip out a calculator and figure them out. I'm going to do it in closed form since I don't have a calculator. To solve for sine B, I'll just multiply both sides by the sine of 81.8. So side B looks like the left-sided fraction, 42.9 divided by the sine of 32 degrees. Multiply both sides by that, puts the sine of 81.8 degrees here. So there is length of side B. When I wrote this problem, all of my numbers had at most something to the 10ths place. So if you do this on a calculator, round to the 10ths place. And so I did it earlier in my life, and I got side B to be 80.1 centimeters. Okay, keep it to the 10ths place because of the 1 decimal earlier. If you do use your calculator, you'll probably need it on your web work. Put your calculator in the degree mode. Get it out of the radian mode, make sure it's in degree mode. For the test, you could leave your answer like that. But I know WebWork wants precise measurements with the right number of significant digits. But again, you know how reliable WebWork is. If you think you're entering the right number of significant digits and you're not getting the right answer, throw another place on the decimal until it takes it. WebWork is very weird. But for me, you could leave it like that. Okay, now we need side C. So I have information about side A. We found angle C, so I can use this similar type of relationship, but put side C over the sine of C. So our third one, our third piece, we'll get C, get the little c, using the fact that A divided by the sine of A is equal to C divided by the sine of angle C. So A was the 42.9. Angle A was the sine of 32 degrees. Sine C is what we're finding. And angle C we found earlier to be 66.2 degrees. And so we'll do what we did before. Just take both sides and multiply by the number underneath that missing side, and we have side C. Side C is 42.9 divided by the sine of 32 degrees times the sine of 66.2 degrees. And if I get you that number from here, I get 74.1 centimeters. 74.1 centimeters. Now, one thing that is a fact about triangles is that the smallest side is always opposite the smallest angle, and the largest side is opposite the largest angle. So to make sure that you did the little bitty algebra steps and the number crunching correctly, make sure it lines up that way. In our picture, the largest angle was the 81.8 degrees, and we got for side B 80.1 centimeters, and that is larger than the other two sides. So let me put it up here. That was 80.1, and I'll put it in a red box, and that we found it. We found angle C is 66.2, and we found side C is 74.1. So the smallest side is opposite the smallest angle. The largest side is opposite the largest angle. We should feel good about it. Okay? Very straightforward formula to use. Easy to remember, but I'll give it to you. Okay, so what was that example? That one was angle, angle, side. Angle, angle, side. Side, I said. All right, so my next one. I'll read it to you and then I'll write it. An engineer wishes to measure the distance across a river. But this is like a real river, not a Texas river that you could walk across. It's a real river. So he can't cross it to measure it. So what he's going to do is he's going to put 2 points on his side of the river, call them points A and C, and then a point B directly across from C on the opposite side of the river. So he doesn't know how that, he doesn't know that length, but he can just survey a point over there. He can measure the angle from on angle C, and he can measure angle A, and he wants to, and he knows how far apart A and C are, and he's going to use that to figure the distance across the river. So let me write it. An engineer wishes to measure the distance across a river. Here's the river. He's on one side, so let's put him over here. Or she, my female engineer. From points A and C on his right, he's going to measure from points A and C. So from points A and C on her side of the river to a point B directly across the river. She measures angle C to be 117.2 degrees and angle A to be 28.8 degrees. So let me put those in here. Let's put C, A. She also knows the distance between A and C is 75.6 feet. This length here. Now point B is over here, so that, let's see, angle C is going to have a measure of 117.2 degrees. Now, how am I going to draw this? My river should have been a little bit more crooked. So that's 117.2 degrees. Needs to be a little bit bigger, like that. There's point B. And from point A, the angle is 28.8 degrees. And we want to find this length here. Find A. So the river should really butt up to those points. I just couldn't draw it that way. Find the length of A. So look at the sequence of parts that you're given. I gave you angle C and angle A and the length of the included side. So we call that one angle, side, angle. Okay, this is the angle, side, angle case. Again, we're looking for a side. And I can have this angle pretty easily. And we're going to need it because I always need to pair my sides and angles up that are opposite of each other to use the law of sines. So our first task is to find the measure of angle B. We will need angle B before we can use the law of sines. Page number am I on? Page 3. Angle B before we can use the law of sines. Again, the measure of the angles have to add to 180. So the measure of angle B is going to be 180 minus the sum of the other two angles, 117.2 plus 28.8. So let's see, I'm going to add those two guys up in there. 8 plus 2 gives me a 0 here, carry the 1. 8 and 7 is 15. The one that I carried makes me a 16. Carry another one, 2, 3, 4. I think I'm at 146. Take 146 away from 180. Maybe I'm at 34 degrees. Then back in our picture, let me just put our picture back here. Here's C. Here's A. Here's B. This number was 75.6. We have this now is 34 degrees. We need this side, which is opposite A, and angle A is 28.8. So I've got the two angles and two sides opposite them labeled. Let's write out the law of sines. It'll say that little length A is to the sine of angle A, as the little length B is to sine of angle B. Now let's put our numbers in there. A is what we're looking for. Angle A is 28.8. Little b is 75.6. And we just found angle B to be 34 degrees. And so as before, we multiply both sides by the sine of 28.8, and we get the length of A. They're all this easy. Pair up the angle, sine of the angle with the side, sine of the angle with the side. Line them up according to what you need to find. Okay. Let's see if there's a case I need to do next. I got the decimal if you ever need to go back and check your answers. I get the length of A is 65.1 feet. Bearings. Well, let's see, I did. Let's do this next one. Let's draw a triangle to look like this. Let's make it really wide like that. Whoa, baby. I'm going to give you, this is 9 feet. This is 12 feet. And the big angle in here is 127 degrees. And let's see if we can find the other two parts, or the other three parts. Let's call this A, B, C. And let's see if we can find angle A, angle B, and side C. What sequence of parts is given in this picture? Side, angle, side. You've got a side, the included angle, and the side. So there's only one and only one triangle that has this sequence of parts. I've got the side opposite of angle A, but I don't have angle A. I've got the side opposite angle B, but I don't have angle B. So I'm in a conundrum, huh? I don't know how to get those other angles. You see the problem? I can't set up my ratios. Let me write my 3 ratios. I have, I'm going to put the signs on top this time. The sine of angle C is to side C, which we don't have. The sine of angle B we don't have, but we have side B. And the sine of angle A, well, we don't have angle A, but we have side A. These 3 things are equal, but now let me put the numbers where I know them. I have 127 degrees here, but I don't have this length. I don't have angle B, but I do have this length. I don't have angle A, but I do have that length. There's no way I can take any pair of those and have an equation that just has one unknown. If I group this pair together, I have 2 unknowns, side C and angle B. If I group those 2 together, I still have 2 unknowns, side C and angle A. And I don't know what the last one was that. There's still 2 unknowns. So the way I've presented this example is that the law of sines is not useful to us here. We'll need one more angle or one more side in order to proceed. I can't use the Pythagorean theorem because it's not a right triangle. So I've got to show you now the next one, the law of cosines. The law of cosines is a little bit harder to remember. takes a bit to derive it too. It involves making all kinds of different right triangles. So I'm not going to derive it. I'm just going to show you the 3 different versions of the law of cosines. So let's leave a blank right there, or let me just put this statement. So here, to save the day, is the law of cosines. Three statements of the law of cosines. Okay, the lowercase letters again represent the sides, the capital letters represent the angles. So one statement of the law of cosines says this, that a squared is equal to b squared plus c squared, which would be the Pythagorean theorem if we had a right triangle. But if it's not a right triangle, we have this additional term, which is minus 2 times bc times the cosine of angle A. So it says that a squared is equal to the square of the other 2 sides minus twice the product of the other 2 sides times the cosine of the angle that goes with the number that's over here. So I can write it a couple of other ways. I can say that b squared is equal to a squared plus c squared minus 2ac, these 2 letters, and then the cosine of angle B. And then the other way would be c squared is b squared plus a squared minus 2ab times the cosine of angle C. We have sides A and B. Those are the 2 we know, A and B. And so I'm going to use the third one. I know A and B, and I know angle C. So that's going to give me side C. Let's go back to our example. So in our example, we know side A, side B, and angle C. So we will use c squared is equal to, let me put it in alphabetical order. That bothers me the way I wrote that. And that'll find us the value of C. Does that make sense? It's a magic formula. I'm not going to derive it for you. You're just going to have to believe it. It's derived for you in your book. All right, let's implement it. Let me go to the next page. Got to keep numbering my pages here. This is page number 4. Page number 5. Copy that down again up here. C squared is a squared plus b squared minus 2ab cosine of C. So C squared is a, which is 12. 12 squared plus 9 squared minus 2 times 12 times 9 times the cosine of angle C, which was 127 degrees. I don't have this one figured out. I need to pull up a calculator. Let's see if I can find me a calculator somewhere. Oh, come on, this space bar doesn't work on this thing. This is in degrees. Yes, that it in degrees. All right, so let's do this. I'm going to punch those numbers in. 12 squared plus 9 squared. I could do that in my head, but I'm not. Minus 2 times 12 times 9 times the cosine of 127 degrees. Enter, enter. How do I do that? Answer. Didn't like that. Not that. Oh, fudge. I want to give it to me. Oh, we got it. We got it. It's hidden in there. Okay, so that is c squared. Pencil. I'll come back and I'll show this to everybody. C squared is 354.99 and 204. So C will be the positive square root of that. And so let me raise that. I want to take my answer. Next one, I want my answer. I want the square root of the answer. And there it is, 18. And now I did 1 decimal place. Let me look how many decimal places I did on this example. I have a 9.0, so I'm going to do 1 decimal place. So C is going to be 18.8. Back here. All right, so C is 18.8. And now let me draw my triangle and show you what we've just found. We have 12 feet here, 9.0, 18.8, and 127. We can get any of the other angles by going now back to the law of sines, or we could use the law of cosines. The problem with finding an angle using the law of cosines is you got to peel all that junk away, and that takes a few more steps than if I just now use the law of sines. So now I'm going to go back to the law of sines to find the angle. So let's find angle A. So I'm going to put the missing term that I have in the numerator. I'm going to put the sine of angle A up here and side A there. And then the pair that I'm given is angle C and its side. So I'm going to set that equal to the sine of angle C and its side. So I don't know angle A. Length A is 12. Angle C is 127 degrees. And side C is 18.8. So to get angle A, I first solve for the sine of angle A by multiplying both sides by 12. Now I need your help. How do I find the measure of angle A? I have to use the inverse sign. This is where inverse trig functions come into play. The measure of the angle is the inverse sign of the number on the right-hand side. And so angle A would be the inverse sine of all of this stuff. So let me see if I can get that measure on that calculator. Get an inverse off of here. There it is. I want the inverse sine of 12 times, let's just try that. The sine of 127 degrees, sine of 127, and then that's divided by 18.8. And I'll close off the parentheses up here. And it looks like it is 30.6 degrees. See that right there? And then how do we find angle B? Yeah, angle B is 180 minus the measure of angle A, which is 30.6 degrees, and angle C, which is 127 degrees. So angle B is 180 minus, let's see, there's a 0.6. 7 plus 0 is 7. 2 plus 3 is 5. And then a 1. So let's see. I got to line this up again. I'm not feeling the numbers today. Four, 2, 2, 22.4 degrees. Angle A was 30.6. I'm putting them in here to make sure that the longest side is opposite the largest angle and the smallest side is opposite the smallest angle. I feel confident here. Do you enjoy that one? Yeah, I really don't know how we're going to do this on a calculator. Maybe try with a calculator. All right, let me find you another one. I'm going to give you some variety here. That was a side angle side. That's a side angle side. I don't want to do that one. All right, let's do a side, side, side. Oops. There we go. Scoot you over. Scoot you over. Smaller. Okay. All right, I'm going to give you a triangle whose 3 sides are given. So let's see. Let's see, this is 6 feet. This is 9 feet. And this is 11 feet. And let's say that this is angle A, B, C. And I want you to find angle A to the nearest degree. Okay, so you can see again that the law of sines is going to be missing too many knowns. The law of sines has the sine of the angle divided by the side, sine of the angle divided by the side, sine of the angle divided by the side. We would, in every single pairing of those proportions, have two unknowns. So we're going to use the law of cosines. Cosine says that if you're looking for any angle, you can take this side that's opposite that angle and put it over here. And then the non-included angles would be part of the formula. So I'm going to write the top one out, and we're going to try to fill in all the parts here and use our little calculators. Okay. So to find cosine of A, we're going to use the A squared is B squared plus C squared minus 2BC times the cosine of angle A. This is going to be side A, opposite of B is side B, and this is side C. Yep. So with this particular side, if you're missing too many angles, then the law of cosines is what you want to use. The last example, we had one angle, but we didn't have the right sides lined up for us. So we're going to have numbers everywhere except for this last one. So we're going to have to solve for this term once we fill our numbers in. Let's grab them. A is 6, so over here I have 6 squared. B is 11. C is 9. I'm going to go ahead and do some of these numbers. I can square all three of these, so let's go ahead and do that. 6 squared is 36. 11 squared is 121. 9 squared is 81. Let's see, 2 times 9 is 18. 18 times 11. Do you guys know how to multiply by 11? Let me show you. Not doing it that way. To multiply by 11, to multiply a double digit by 11, copy down the first digit, copy down the last digit, and then add the two digits together, and it goes in the middle. So 11 times 18 should have a 1 here, an 8 here. 8 plus 1 is 9. Should be 198. Is that pretty sweet? Maybe I made it up. No, I didn't. All right, we're going to solve this for the cosine of A. 121 plus 81 is 202. So I have 36 is equal to 202 minus 198 times the cosine of angle A. I'll have to subtract 202 from 36. Looks like I'm getting 166, and it'll be negative. I got a negative on each side, so I can cancel the two negatives. I'm going to take 166 and divide it by 198. And that's going to give me the cosine of angle A. My job was to find angle A. What's the next step? Take the inverse cosine of that number over there. So we have that angle A is equal to the inverse cosine of 166 divided by 198. So this one you could leave like that. You wouldn't need a calculator. It's calculated for me as 33 degrees to the nearest degree. So we're rounding up. Okay? Did you understand the algebraic steps to get the cosine of A by itself? I'll do the ambiguous case next time. Let me find one more example for you. I want you to get your money's worth. Grab one that's worked out for me. This case. Angle, side, angle, 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 side, 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 angle, side. 1, 2, 3, 4. We did all the 4 biggies. So let me put one down here and you tell me which one we got. Okay, so there's our picture. Which of our triangle congruence theorems do we have here? Angle, side, angle. Got an included side, butted up by 2 angles. So there should be one and only one triangle possible. Do we need to find anything else? Looks like we are going to need angle C first. Because if I try the law of sines here, the A goes with the sine of 37, the B goes with the sine of 48. So I don't know A and B, and I don't have angle C, but that's the quick and easy one. So quickly find me the measure of angle C. Let's see, 48 plus 37 is 88 minus 3 would be like 85. And so if I subtract there, I get 95 degrees. We'll put that here in red. The law of sines is so much shorter and easier. I'm going to use it. So the pair that I have is angle C and the side opposite angle C. I'm looking for sides, so this time I'm putting sides in the numerator. So I'm going to write my law of sines as C divided by the sine of C is going to give me A divided by the sine of A. And to get the other angle, or for the other side, C divided by the sine of C is going to give me B divided by the sine of B. You like that? Whatever you're looking for, put it in the numerator. You'll still do the cross multiplying step, but if it's in the numerator, it saves you 1 step. Okay, so let's put the numbers in here. We have the 18 and the sine of 95 degrees. Over here, the little a is what we're looking for, and we have the 37 degrees. So all of those numbers are calculatorable. So I'm solving for a by multiplying both sides by the sine of 37 degrees. Now we'll fill this one in up here. Same ratio to start with. 18 divided by the sine of 95 degrees is equal to B. B we don't know. We're looking for that but angle B is 48. Again, one step solves for B, multiply both sides by the sine of 48. So this kind of problem right here would be real easy to put on a test without having to worry about having a calculator. I don't know if you guys enjoy calculators on tests. I don't like having a calculator on a test because then you'll give me decimal answers and I got to check all them. So you would leave your answers like that. However, on WebWork, you do have to enter decimals. You good with that? Did everybody get a chance to put their name on that piece of paper coming around? It's there before you leave. Put your name on there. Everybody good? Ready to go home, pig out? If you can't go home, come to my house. I'm cooking for the first time in many, many years. It should be a horrible experience, but that's okay. I've got plenty of bottles of wine. About that first. Happy Thanksgiving, everybody at home. And I'll get your test graded soon and put on Blackboard.